yourself, Simon.
Oh, absolutely. Sorry, it's a little bit broken, and I apologise if there's any noise behind me. It's gotten really, really windy here in the last 10-15 minutes, so we're expecting quite a blow from the northwest tonight. So my name's Simon Lewis. For those of you who don't know me, I'm an astrophotographer. I live down here in the South Island, just outside Christchurch, in a small place called Greendale. I have my own observatory here at home, and spend a lot of time doing astrophotography, mostly of nebula. I'm also the vice president of the Canterbury Astronomical Society, and as you can tell by my accent, I'm an import. So you'll understand that the last few years have been getting to know the night sky down here in the south. Because it looks very, very different to the north. And in fact, I look at the night sky in the north now and go, where's the cross? I can't find my way around at all. So it doesn't take long to get very, very familiar. Alrighty. So let me just kick up this presentation. Hopefully you can see all that. You guys see the presentation okay? Cool. So one of the things that's interested me over the past few years has been fast refractor imaging, and this mostly because the short windows that we get in our weather down here in the South Island a lot of the times. So I have to maximize the amount of data I collect in very, very short time frames. So slow scopes and long nights of imaging aren't something that I can really achieve. I have to get in there, grab the data, maybe over one or two, and that is me. I might have to wait some weeks again before I get another go. So most of the refractors on the market these days are relatively fast, but they're mostly around, certainly at the focal lengths that I'm using, around sort of f7, and that can be much speeded up these days. And so we're going to have a look at these fast refractors, how you can image with them, but also the trials and tribulations that you get with these, because they do come with some challenges. So like all of my presentations, I like to start with a little quote, and Abraham Lincoln came out with a great one. He said, the problem with quotes found on the internet is they are often not true. So so a wise man, that Abraham Lincoln. Alrighty, so so as I said, there is a speed revolution going on at the moment. Computer-aided optical design and combined with modern optical manufacturing is creating a whole new generation of these fast refractors on the amateur market, and you can find these mostly from companies like Sharpstar. It's very much driven out of the Chinese optical factories, and there's been a real push to get faster and faster, and they're certainly on the verge of breaching f3 now. And this used to be the domain of sort of, fast imaging Newtonians, and something, a lot more like the more unusual optical designs like the RASs, the Roackerman Schmidt-Cassegrains. These refractors, they really, really reduce the imaging time required, and we'll talk a little bit about that as we move along. But they do come with some challenges. They can be difficult to tune, and there are some little bits of information that can help you if you decide to go down this path. And certainly, I've had plenty of hours pulling my hair out and spending some evenings trying to tame them. So hopefully this information will help you smooth your entry into the fast refractor imaging world, but it's certainly one that has been an exciting path. So what is a fast refractor? How do we choose one for your own needs, and how does that refractor impact other components within your system? So obviously we've got a lot of other optical parts around our imaging systems. We've got cameras and filters, flatteners and reducers, etc. So building up a system around these, it kind of goes together like a Lego brick. And how do you tune them? Because if you take a telescope off the shelf, buy a monochrome camera, a bunch of filters, a flattener, etc. You'll find some issues and problems as you move along. They're not perfect, but if you spend some time tuning them, then you can get some really, really good results. So I'll show you how to look at that. Cool. So just reminding ourselves then, and for most of us in the room, this probably makes complete sense. This presentation was done to a more general audience, so you'll forgive it if I'm trying to teach you to suck eggs. But broadly speaking, the F number is the ratio of the focal length to the aperture involved. So we know that, for example, if we've got a 550 millimeter focal length and 100 millimeter aperture, that gives us an F ratio of 5.5. And these kind of numbers are fairly common across optical systems. Everything from camera lenses to telescopes and accessories. You'll find these numbers all over our equipment. But in general speaking, the smaller the number, the faster the scope, and that means they gather light quicker for a given exposure length. So if I had a scope where I was doing 1 hour of exposures, and I've got a scope of f10 or one of f4, you will gather a lot more light with the f4 numbered focal ratio. So that's pretty much how they lie. But I'm sure most of you in the room will be aware of that. Okay, so it's all good having fast scopes, but there are some positives, but there are also some downsides to these, and it's how we tame these as we try and put our systems together that will help you be successful. So just on a broad scale as well, in general, as you move through the range of telescopes that are on the market, on the right-hand side, you've got the general sort of Schmidt-Cassegrains out at f12, relatively large aperture, but relatively slow optics. So a lot of light gathering capability, but relatively slow in terms of actual capture speeds. And as we move to the left, you've got the typical sort of edge systems around f10. Then you're moving into the realms of certainly in the top there in terms of reflectors. You're talking f8 for things like the smaller Schmidt-Cassegrains, the RC type telescopes that are common for astrophotography, and then moving further left there down to f4 with the sort of imaging Newtonian, the astrographs. And then the really crazy speed at f2s. These are the Raza. These are this Roe Ackerman ones that Celestron sell. These are down at f2. Great as in terms of speed, but absolutely insane in trying to tame these things in terms of things like tilt, etc. In the refractor market, most of the commercial larger end focal lengths. So I run telescopes of 120 to 130 millimeters. These are mostly around sort of f7, and they are relatively quick, but they still not as fast as the shorter, wider refractors like the FRA 400, the little ASCAR 70 millimeter refractor that I use, which is down at actually f5.6 as a off the shelf without the reducer. And then you've got the likes of camera lenses, and these are generally very short focal lengths, but relatively fast. Modern optics in these systems now. I think the last one I was looking at was a 1.8. I think there's 1.5s. There could be even faster ones that are on the market. I'm not really a camera lens maniac, but in general, what these all have in common is that as you increase focal length, the slower the optics, and unless you go for really super size multi-meter size scopes, but for the amateur market, certainly as you move more towards the longer focal lengths, the slower that they get. So invariably, fast refractors are going to be generally much wider field of view, and as you move closer to longer focal lengths, then the speed will slow down. So if you look at the underneath the f5 there's an Esprit 100, which is a Skywatcher. It's got 550 millimeter focal length. If you go up to the 120 millimeter of that range, they're up to f7, so they take a bit of a jump. It is possible to get slightly faster, larger scopes, but the price goes up astronomically. It really does go up very, very quickly and very, very sharply. So for those of us that can afford these kind of scopes, this is kind of what you're looking at. So how do you choose one of these refractors for your own use? Well, there's a few things that you need to think about. One is size. Are you going to operate fixed on a pier in an observatory where you're not going to be lifting this beast on and off a mount every night? Or do you want something that is portable, wide field, and will fit in a backpack, for example? So there's a big range in between. I certainly, my Esprit 120, I would not want to be lifting this on and off of a pier every night or on a tripod. The scope itself, with the Moonlight Nightcrawler and the Eagle imaging cameras, etc., and the reducers, it's close up to about 16, 17 kilos, and you really don't want to be lifting that on and off a tripod every night. So that's pier mounted. But if you were backpacking and you wanted something quick and lightweight and wide field, then you could get yourself a nice small camera lens on a small portable tracker, and that would give you a really fast wide field imaging capability. But they're very, very different in terms of what you get out of them. So the other thing there then is mount capability, because if you've got a camera tracker, you're not going to be putting 100 millimeter Esprits on that. Likewise, if you've got a large equatorial mount that's on a pier like I have, then you can really start to push the size of scope upwards. So you can get much larger aperture refractors and drag more light in. And then if you can speed that up as well, that'll really start to be a bit of a light bucket. Camera specifications is also important. We'll talk a little bit about pixel scales, etc., in a minute, because that's something that you do need to think about. You also need to think about whether you're using a dedicated, camera like a ZWO or a QHY, a cooled camera, something with much smaller pixels, for example, if you're going wide field, or bigger pixels if you're going longer, or whether you're just going to stick with a DSLR or a mirrorless camera. That you need to have to think about the specifications, pixel sizes, sensor size, etc. The big plus about having cameras that are cooled is, of course, then you can do cooled dark frames and calibration files that will really help you in the processing as well. And yeah, we're talking about the field of view there. What objects do you want to image? Are you a nebula hunter like I am, where you want relatively wide fields at some time, or are you a galaxy hunter and want something close up with long focal lengths and relatively large pixels? So that's something you need to have a think about as well. And of course, what's the budget? Because full frame, relatively small pixeled cameras can be eye-watering. If you move up to something like an FLI, which is almost observatory grade equipment, then you start getting into the tens and twenties and $30,000 price range. But even the smaller cooled cameras, you can say goodbye to $3,000-4,000 on one of those quite quickly. So let's take a quick look at this piece around here. The sort of camera specifications. What field of view you're going to use, and what are the pixel scale are you wanting? Because they make a lot of difference to the quality of your image. So just to remind ourselves then, or for those who may not be familiar with the term, pixel scale basically it refers to the amount of sky that one pixel of your camera sees, and it's measured in arc seconds per pixel. And if you think about angles, angles are generally traditionally split into minutes and seconds. And in this case, we're not talking about time, but a fraction of an angle. So 1 arc minute is a 60th of a degree, and 1 arc second is 1/60th of an arc minute. So that can be quite hard to think about. But if you think about this, one arc second is the size of a small coin at a distance of about 3 to 4 kilometers. So that's the kind of size that you're looking at. So a lot of us who do astrophotography, we're always aiming to get our guiding, extremely small. When we start talking sub-arc seconds, that's the kind of distances that you're looking at, and the kind of angles that we're dealing with. It really is kind of very, very tiny. So our atmosphere limits the resolution that we can achieve in our images for most locations within New Zealand. Even on a good night, the seeing will be about 2 arc seconds, and this is because basically the atmosphere is blurring the stars. If you were above the atmosphere, the stars are much smaller. Their angular distance is less than an arc second, but we'll never see them like that on the ground because of the blurring effect of the atmosphere. So unless you live on the top of the Atacama Desert and have sub-arc second seeing, most of the time in New Zealand it's bigger than 2 arc seconds. It's probably more like 4 or worse. So when you look up at the night sky and it looks like you're looking through a swimming pool, that's exactly what's happening here. You're basically getting blurred by seeing. And the longer the focal length of the scope, the smaller the arc seconds per pixel. And likewise, the shorter the focal length, the larger number of arc seconds per pixel. And that plays a big role because you want to match the camera and the telescope to have reasonably good pixel scales, so that you are not either oversampled or undersampled. And we'll just talk about that a second as well. So just looking at those combinations then. So the telescope and the camera pixel size is the one that you need to be looking at. The more pixels you have, the more the light falls across more of these, and the less sort of clarity you get in them. And that alone doesn't set the field of view or the resolution. It's really is a subtle balance between the pixel sizes, the sensor size, and the focal length. And there is a little formula here as well. I put it in, and I'm sure that you can have a look at these. But basically, the pixel size in micrometers, microns of the camera, divided by the focal length of the scope, times 206.3 is the angular resolution in arc pixels. Now, if you're like me, I jump around playing with different types of telescopes and focal reducers and different cameras and filters. I don't want to have to be calculating this all the time. And we're really lucky in that there's two really good websites that you can use to play around with these things on the fly. One is the astronomy.tools calculator, and the link is in there for you to have a look at, which is the top one. And there is also another one called Blackwater Skies, and that's the imaging toolbox in there. And on both of these, you can play around with different cameras. They usually have the standard models of cameras in there, and the standard telescope with all the focal lengths already loaded. And you can add things like focal reducers or flatteners, etc., to see what the impact is on the field of view. So if you look on the bottom picture, you can see the big green box, and that would be the field of view that camera would see. But also you'll be able to see what the pixel scale is to work out what the sampling looks like. So I would highly recommend those two if you want to get into to having a play around to sizing up different telescopes and different cameras and the effect of things like focal reducers, etc., on speed and on field of view. So we talked about undersampling and oversampling, and it's really important to choose the right pixel scale. And that's, as we said, it's a combination of the focal length and the pixel size. And what happens is if you get this wrong, then the light from your star will fall over many pixels, and you'll end up with bloated stars, which is oversampling. And you can see that effect on the left-hand side of those two images. And you can in some way fix that in post-processing with a process called deconvolution. But in general, if you look online and you have a look at cameras of smaller pixel size on longer focal lengths, you can see the effects of oversampling. It generally looks a softer image. And consequently, at the opposite end of the scale, if you have stars that don't cover enough pixels, you end up with these sort of blocky stars. And if you look on the right-hand side of that image, you can see the effect there. And the way you'll see that is if you zoom into an image, you'll suddenly see that a star becomes just a blob of squares. Because basically the star hasn't covered enough pixels, and you'll end up with square boxes. So as a general rule, you should be aiming for about 1 to 2 arc seconds per pixel to give you best sampling over most conditions. You'll get some nights where you could push it, and this is probably one for somebody that's got a very long focal length and smaller pixels. Sure, you can get away with it, but the number of nights that you'll be able to get away with it over a year, you'll know yourself of how many really good nights we get. Consequently, on the other way, if you go the other way and oversample, then you will have some challenges in post processing. You can get away with a thing called drizzle, which is basically a kind of resampling to put some of the data back in. But it is better if you kind of stick to the general rule. Okay, now let's just have a look at what that really looks like. Now you'll see in this image We've got a fairly atypical ZWO camera, an ASI 2600 and MC or the MM. They're both the same resolution, and they both have a pixel size of about 3.76 micrometers. And you can see in the middle, hopefully it's showing up on the presentation, but you can see that the numbers around the center band are orange, and they to the left of that, they're sort of lighter grey, and to the right of that, they're a more darker grey. And that the key is at the bottom there. So basically, in the middle, the orange ones are basically the ideal resolution. Now you'll notice that they vary. It's not a one and not a lot else, or two or not a lot else. There is a band really that you can operate around. So if we take for an example of that, at 700 millimeter focal length, and we use this camera, which is the about f3.7, you would see that the pixel scale would be somewhere about 1.18, which is a relatively good place to be in terms of sampling. Now, if you went for a really short focal length, so for example, we use an FRA 400 with a reducer that's got a 280 millimeter focal length. You can see for that same pixel size, you're actually heading towards a pixel scale of 3, which is starting to become quite undersampled. So that means that you would end up with stars that are quite blocky. If you go the opposite way, if you were to put that camera with 3.7 microns on a on an RC at say around 1200 millimeters, you'll see that the pixel scale now is down at 0.6, and you're starting to become quite oversampled here. So that's not to say that you couldn't use that, and either way, but you've got to be aware of what you would have to do to manage it and get the best results out of it. So you would really want to choose a camera like the 2600 for something around anywhere between sort of 350 to say 700 millimeters, which covers most of the sort of mid-range refractors on the market. So that is something that you need to take care of. And of course, when you start adding a focal reducer, that will drop the focal length again, and then you might be quite okay without the focal reducer. But when you put the focal reducer on, then you start to be heading into the undersampled area. So here we are. Sits between 3.5 and 4 microns, and basically that's the area that you would be looking to operate in for that camera. So it would give you a rough idea. You can push the edge, so you could quite theoretically, push that camera out 750, 800, you'd still be okay out there at 0.9. Once you get above that, then you would be starting to get into the oversampled territory, and that's just something you just need to be aware of. All right, so we look at the 294 mm. This is a pixel scale of 4.3, so this is quite a little bit bigger pixel, and same path. But you can see here that you could actually use this quite comfortably on, up to maybe even 1,000 millimeter focal length, or even a little bit more. But if you were using something wide field, like a camera lens, you can see that, you would be very, very undersampled at the bottom end of the focal range. So that this probably wouldn't give you the best outcome. However, some cameras are very clever. So if you look at this camera, this is the 294 mm again. This is the mono version of this camera. You can do a little bit of a clever thing on this camera, which is that you can actually take the resolution up to 8288 by 5644 size pixels, and with a pixel size of 2.3. This is done in camera, and there is a slight trade-off for it. The bit depth is slightly less, so in terms of grayscales, you will lose a little bit, and what we call the full well. This is the amount of light that each pixel can accept before it spills over and ignores any more, is reduced to 14,000, and that's a little bit down. If we go back to that camera, you can see that it's got a full well of 50,000, and so this you would be able to expose for longer on this camera without blowing out details within bright objects. Go back to this one then. So this has got a pixel scale, pixel size of 2.3 micrometers. This is really, really good. If you use this on a wide field rig, you could get down to maybe 250 millimeters, even 200 millimeters, and still be relatively well sampled. But anything longer, you're going to run into trouble because you will soon be oversampled quite quickly on this. But if you've got the 294 you can multi-purpose this. You can run bin 1 on something wide, like a red cat or a camera lens with an adapter, and then use it on a longer focal scope, just using bin 2, which is the normal mode. Cool. Some other things to look out for when you're choosing cameras, and you can see that I've got affliction to red tins, which is one of my interests. So other things to look for, there is this term called QE, which is quantum efficiency, and this is the efficiency at which the sensors, the pixels, turn photons into electrons. This is really something that you want to have a look out for, because if we take the ASI 1600, for example, in the middle, and we compare that to the ASI 2600, the 2600 has got an efficiency of 91%. So that means out of every 100 photons that hit the sensor, 91 of those will be turned into an electron count. Whereas for the 1600, the efficiency is only 60%. So you're only getting half of the number of photons turned into to an electrical charge to be counted. So that means there's a 31% difference between those two cameras. So if you were to put these on the same scopes and the same focal lengths, you would, in the same type amount of data, you would have a 33% reduction in the amount of imaging time. These kind of changes mean that I can capture as a one channel of data on the 1600 in a night, because I generally do sort of 8 to 10 hours per channel. If I use the 2600, I can almost, in fact, in the middle of winter, I can actually squeeze 2 channels in to one night, because I can capture the same amount of data that I would take all night on the 1600 in about 6 hours. So that means that's a huge change in speed. So that's something that you really want to think about, is that quantum efficiency. Other things to look out for then, well depth. We talked about that earlier on. This is the amount of light that will the pixel will accept and store information on before it overflows. Now, those of you who've been around a bit will remember the old CCD days. If you exceeded those well depths, then it would start to bleed cross channels and lines in the sensor. And doesn't happen these days. They have anti-bleed technology in the CMOS cameras here, but it does mean that basically you would start to blow out the details. So if you were imaging, for example, Orion, and you exceeded the well depth, then you would get blown out cores of the nebula. Having said that, the 2600 is very, very well placed at 50,000. You would find that I certainly can image the tarantula in narrowband on the 2600 with 120 millimeter and do 15-minute exposures and be nowhere near exceeding that well depth. They really do well. Other thing to look for, but maybe not quite as important unless you're really pixel peeping, and that is the bit depth. So the greater the bit range, the more levels of gray that you will see within the image. It's the old 12-bit sensors. I can see some of the level of detail in 12-bit sensors now versus the sort of 14-bit. But you would be really, really challenged to, unless you really went in and started pixel peeping. The 1600 is an older camera, but it can turn in some fantastic images still, and still wins a lot of awards even today. So don't write it off just because it's a 12-bit conversion rate. The 16 bits are nice, and you do get a lot more gray levels in your images. But don't write the old cameras off just yet. One of the last things to talk about is the read noise, and this really lower read noise really is the noise imparted from the camera electronics, and this is one area where you can see some difference these days. The ASI 2600, for example, is a very, very low read noise. When you capture a 15-minute sub off this kind of camera, there is almost no noise in the image. It almost looks like film. It's extremely low noise in terms of the actual electronics, whereas the old 1600, you would definitely have to do some noise reduction on those cameras, but they're still good. And you can see there on the left-hand side, the ESA 183 was almost the first generation called camera, is a little bit noisier again, but still has its place because it's got 2.4 micrometer pixels. So if you were doing wide field, short refractors, or camera lenses, that's still a good lens to look at, and well sought after on the second-hand market at relatively low cost. So one to look out for. So we talked about our refractors being sort of f7. So how do we make these things go faster? The scopes themselves, as they come off the shelf, almost invariably, if they're higher end devices, will have some kind of flattener, field flattener in them, and that will allow you to have nice round stars across the whole field of the image. But many offer a focal reducer as well, and we should have a kind of look at what those focal reducers do. And so we look at the little FRA 400 here with the ASI 2600, and it has a relatively good field of view native. It's got a focal length around 600 millimeters, and as a sort of typical sort of 70 millimeter refractor. And you can see on the bottom here that the resolution is 1.29 arcs per pixel, so quite nicely sampled. It's got a focal ratio of f5 5.6, so it's relatively quick, and got a field of view of about 2.4 by 1.5 degrees, which is quite a wide field. If you look at this picture of Orion here, you can fit Orion in it comfortably. Now, 5.6, we can go faster than that, and we can do that by adding what's called a focal reducer. So this is a fairly atypical one. So the FRA here is a 5.6 off the shelf, but if you add this focal reducer, this is going to take the speed of this refractor down to f3.9. So that's a significant reduction from 5.6 to 3.9. It's about 64%, I think, something like that. And that means that you to gather the same light, you only need half the time. So that really will improve things. But what are the other side effects? Well, if you put the focal reducer on, sure, you go down to f3.9. The resolution, that arc per pixel is now 1.84. Still well sampled. Still quite acceptable. You may need to do a little bit of post processing on the stars, but at 1.4, generally the stars will remain round and relatively well sampled. Here's the big change. The field of view has gone from just about fitting Orion to a huge leap in field of view to a much larger 3.2 degrees by 2.14. So the effect of the focal reducer then is, yes, it's going faster. But remember when we were talking earlier on about the effects of focal length, as the shorter the focal length, the wider the field of view, and this is what's happening here. So you're gathering all that extra light from that area in the green box versus the blue box, and that's giving a wider field, but a lot more light being gathered onto the same sensor area. So adding the reducer will speed up the system, but it will give you a wider field of view, and that can sometimes play to your advantage as well, certainly if you're into nebula hunting. How about going even faster? What we have here is a little device from Starizona. These are a manufacturer in the States, and they produce this little beastie, which is the Apex. It comes in two versions. The short version, which is basically up to 500 millimeter focal length, and the long version, the L, which is 500 and above, and can even be used on things like RCs. With these reducers, that sort of 5.5 APO now becomes a 3.6 astrograph, and an RC becomes f5.9, which is considerably speedy. So it provides a 1.5 times wider field of view, but gives you a shortened exposure time by a factor of 2.4. So if you want to go wide and fast, then these are well worth looking at, and they're not cheap. They're about, I think they're about 400 New Zealand dollars. You can get them on the second-hand market, but they've got a reduction ratio of 0.65. Now, this is where things get gnarly, and this is where I started getting into some real difficulties, is that as you get into this zone of speed, you've really got to pay attention to the sensitivity of things like spacings, particularly if you've got optical filters in the path. It's going to be really critical in terms of any kind of tilt or sag. So if you don't have a really good focuser, you might start to see stars in the corners. In one corner in particular, that'll have comed stars that are not round. They're almost like teardrops. And there is no way that you would want to put one of these into an eyepiece clamp, for example. You just would never ever get this to look right, and every time you took it out and put it back in again, you'd be pulling your hair out again. So these really are something that you would want to use, where you can actually screw these into the focuser, screw them into the draw tubes, and have mechanical rings connecting the camera to these, and they come with a variety of different adapters to connect to different types of focusers. But these are really good, and they are really super fast. The one thing that you may also find with these as well, because they are so fast, you may find brighter stars will start to flare, and certainly I've had a couple of images where I've really been pulling my hair out, because no matter where I've seemed to point, they do seem to create flares in certain corners of the image. But that's a downside, where the upside is that you could almost image one image per night on this and have some reasonably good amount of data at the end of it. So that's the apex, which is about the shortest and fastest reducer that certainly for a refractor and for an RC at the moment. So they're worth looking at. Cool. So here's an image I took using the apex on my Esprit 100 here in Christchurch. This is an Aeroband image, and you can see that it really does a great job. This is about 5 hours per channel, and really pulls out the detail. You can see around the edges of the nebula some really faint wispies, and there's a lot of very nice contrast in the middle of it as well. And this is a false color palette image with hydrogen, oxygen, and sulfur. And you can see the star shapes are relatively good, even though it's running at f3.6. Cool. Okay, so we just talked a little bit about filters causing us some challenges, and it's worth having a quick look at those as well while we're at it. So filters in the optics of fast imaging scopes is a really complex subject, and filter behaviors, if you don't buy the right filters and really size them appropriately, you can really run into some very expensive mistakes. So here's some top tips then. So filter specifications, they usually show the f range, the focal range that the filters are designed for. And you really want to be looking at filters that are designed for fast optics. Now, if you're looking at chromas or astrodons or these ones, these are astronomics, this little graph is for, then you can actually specify a lot of the time if you want them for fast focal length. So my chromas, I asked specifically for f3. If you want to use it on a RASA f2, then you really need to be looking at the specialized ones from like BARDA, who have got even faster coatings for those scopes. And this really matters because the faster scopes have an increased light cone, the angles that the light hits the filter. If you get it wrong, you will end up with dirty great halos in the image, and you just will really have a horrible time post-processing trying to get rid of those halos. In general, cheaper coatings will also give you that. And the other thing that will help you as well is that if you get a filter that is matched, the transmission rate through the filter will be reduced. As you go faster in terms of your optics, the transmission rate through them leads to a light loss. So if you don't choose the right filter coatings, the right speeds, and even the right size. So generally, for example, if you look at an APS-C sensor, generally the sensor size is such that you could get away with a 36 millimeter diameter filter. But if you're going to go on these fast optics like we're showing here, you will end up with some significant vignetting, darkening of the corners due to light drop off. And to get rid of that, you would then really want to step up in size to 2-inch filter. Now that has a substantial cost implication. If any of you bought filters, particularly narrowband at this kind of size, you'll know how eye-wateringly expensive they are. So you really need to plan ahead if you're going to, in the future, if you're going to have a go at fast refractors, you're going to want bigger filter sizes for those sensors, depending on what you're using, whether you're using the 4/3 of a 294 or a 1600, or whether you're going to go with an APS-C and you're going to need 2-inch. Now you can imagine going for a full frame camera and a fast scope. You're going to be doing 50 millimeter filters, and so you better have a spare kidney for sale. the other thing that you need to consider with these filters as well is that you must consider the filter thickness, as that adds a length to the optical path, and it's usually you need to be thinking about 1/3 of the filter thickness to the optical path, and add that using spacers. So if you have a 3 mm thick filter, you need to be adding about 1 mm to the back focus by adding a spacer in, and you will certainly see that if you use that apex focal reducer. If you start adding filters in the line, you will certainly see the effects almost immediately in the corners. If you just install that on the scope and don't add any additional length. So that's something that you really need to think about as well. Alrighty. So that's kind of some of the outliers of, choosing the camera types and, some of the focal reducers and the effects of them, and looking at the different types of filters and why you would want them. So how does it all fit together? Well, here's some tips that I put together to kind of help you. Before you press the buy now button, really spend some time using those online calculators. Don't be asked to afraid on any of the forums about how those particular scopes or combinations work, people's experiences of them, and spend some time. If you have a look at places like Astrobin, you can have a look at different sets of filters and have a look at the scopes that they were used. And I can almost guarantee you, if you look at some of these pictures online, you can start to get a feel for which filters are in use for those images, depending on the results in terms of, how much contrast they have, how much light was in the image, and is there any halos around any of the stars, etc. So please, spend time, ask questions, and do plenty of research before you press the button, particularly around filters. A set of LRGB and SHO filters for for a 2-inch camera is going to cost you some thousands of dollars, and you really want to get that right. Many scopes have matching flatteners or a focal reducer are available, and I showed you one there with the ASCAR, and I know that Sharpstar do them. The Esprits now have a matching range of reducers as well, and almost invariably, if you're buying that scope and there is a reducer available, then they're usually a pretty good deal to get the matching one. The only ones I would say just be a little bit wary of, I've had some varied experience of Williams Optics ones, and I've had one or two Explore Scientific ones that where it says it might be a 55mm backspacing, it's not always what it says on the side of them. They're a lot better these days. And generally, the Explore Scientific scopes are on really good quality. I used a 102 for a lot of my imaging when I started, and getting some really good results. When I actually put an aftermarket focal reducer on it, I actually put a Stellar View focal reducer on it, which was really quite a good result. And you can see these were two of my early imaging rigs. A Stellar View 80 on the right hand side, and with a Moonlight focuser and a Williams Optics rotator, and on the left is an Explore Scientific is a 102 triplet, FCD 100 triplet, with an ASI 1600 GT on the end of it, again with a Moonlight focuser. And these are two really good rigs. They've both got Eagle, Primalucha Eagle imaging computers on the top, which is another discovery that helped me use these weather windows, because I can use SGP and then just program this weather window in, and hopefully it will run on its own. So secondhand can also save you money if you're on the market for stuff. If you buy from the right sources, secondhand is well worth it. Cameras are always getting upgraded and traded in, and when those new cameras come on the market, there's usually a clamber to get the latest and greatest models, with people selling off their slightly older models. And as I said earlier, don't discard those. The ASI 1600 is an absolutely fantastic bargain secondhand. You can use 1.25-inch filters. They're generally um, quite a bit cheaper. You can go for 31mm filters if you're going to go faster, in the standard wheels, and they're a reasonable price. But you can still pay, $300-400 for a filter in one of those. More if you buy Astrodons and chromas. Um, Always budget to spend more than the scope and the camera. You will need lots of other bits and pieces as well, filters and filter wheels. If you budget, um, 1.25-inch filters and then have to go to 31mm, that's going to add a chunk of money to your budget. So lay it all out on paper. Have a think about what focal reducer you're going to use and add that in as well, because you really want the ability to have either a full focal length or go fast, to make the most of the cameras and scopes. Do not use clamp fittings. That to me would be one of the biggest learnings. If you try and use clamp fittings like an eyepiece holder in these fast systems, you will end up with all sorts of sagging. You will end up with all sorts of flex, and you will go insane trying to get rid of them. And every time you put the camera away or put it back in again, it will look completely different, and you'll spend time trying to get nice round stars again, only to face it yet again. My systems here are all built up. They don't get broken down. Um, they remain as a tuned rig. The idea is I can just put this onto the tripod, with the head unit, connect up the power, connect up the mount USB, and pretty much be ready to go. I don't have to start putting stuff together and then finding that the system has moved. It doesn't perform the same as I had last time. So that's something that's really, really important. If you can get away with it and you don't have to juggle components, that's a good plan. So, spend time building up the modular system and just get in your own head that you're not going to keep moving the stuff around. The less you move it each time, the more reliable, the better tuning that you'll be able to achieve. And lastly, but least, look, be prepared to spend some hours tuning these things. You really won't get away with just taking this stuff off the shelf, putting it all together, and having, perfectly round stars and no tilt and no sag or anything like that. It will take time. Have a good stock of spacers on hand. Because you're going to need to add some length because of filters, etc. And just remember that if you put in a few evenings of tuning, that will pay dividends in the image quality. Alrighty, that's about me. So quite happy to take any questions if anybody's got any questions. Thank you.
Mainly deep sky objects, between about 1 and 3, I think is suggested, depending on those charts you show. What about if we're doing planetary?
Planetary is a completely different ball game. So for planetary, you really would not be so worried about the speed of the scope, but you're really worried about the getting a really good long focal length and an aperture. So you wouldn't be using these kind of rigs really to be doing planetary imaging. For planetary stuff, you're going to be looking at a long Newtonian or a long focal length Schmidt-Cassegrain, chucking a Barlow in there and getting something like a small planetary camera with video on it, and capture it that way, and you don't really worry so much about the focal ratio. If you've got a long fast Newtonian, that's a boon. But it's these fast imaging rigs are really deep sky. You'd be looking at galaxies or nebula to try and capture these.
Thanks, Simon. Any more questions? Well, from the internet, would you suggest the 1600 mono or the newer 294 mono?
I would suggest the new 294 mono, actually. It really depends on your budget. As I say, don't discard the 1600, because if you can buy one at a very good price and get a filter wheel and some filters with it, and that fits your budget, then certainly don't discard it. The 294 is an upgrade. It has a much better efficiency, and you've got that little capability of doing that bin 1 mode to get a much bigger resolution at a slight discount of bit depth and well depth. But my experience with the 294mm is that in New Zealand, if you're in a relatively dark sky place, then that well depth won't give you any issues, and certainly the 294 has been a cracking camera. If you can get a 1600 and pick up a filter wheel and filters and get a good price, it's a good entry.
No more? In that case, thanks very much, Simon. It was a really, really good talk. I really enjoyed it. Thanks.
Thank you for inviting me.
No, you're welcome.